everyone, my name is Sakshya Yadav. I am a student of Faculty of Engineering and Technology, University of Lucknow. I am going to present seminar on the topic Biomedical Waste used in Civil Engineering and Construction. So, move to the next slide. Index, in which biomedical waste, sources and data, segregation, biomedical waste used in construction industry, and need of this work, concrete, road pavements, and conclusive. Now move to the next slide. Biomedical waste. Biomedical waste is the waste, liquids, solids, sharps, and laboratory waste that are potentially infectious and dangerous. It is a waste from biological sources or is used in the diagnosis, prevention, or treatment of disease. Common producers of biomedical waste include health clinics, hospitals, medical research laboratories, physicians, dentists, and home health care. Types of biomedical waste. Medical waste are mainly categorized into two parts, non-hazardous and hazardous. Hazardous waste include pathological waste, infectious waste, and chemical waste. Hazardous waste are those that may contain toxic substances generated from industrial, hospitals, and some type of household waste. These wastes could be corrosive, inflammable, explosive, or react when exposed to other materials. Pathological waste. Pathological waste consists of tissues, organs, blood, and body fluids. Infectious waste. Waste contaminated with blood and other bodily fluids. Chemical waste. Chemical or pharmaceutical drugs utilized in clinical areas that are hazardous and require more stringent disposal. Sources and data. Medical waste arise from various activities. These include general medical treatment, clinical investigation, food preparations, and ward activities. The quantities of medical waste generated among other factors depend on the status of the hospital, level of instrumentation, and sometimes location of medical facilities. Medical wards, operating theatres and surgical wards, healthcare units, laboratories. According to the Central Pollution Control Board, according to the Central Pollution Control Board annual report of 2016, total quantity of biomedical waste generation in the country is approximately 517 ton per day. India generated over 18,000 ton of COVID-19 related biomedical waste in only 4 months. Now, segregation of biomedical waste. In table number 1, it is chart for segregation. It includes yellow dustbin, red dustbin, white dustbin, and blue dustbin. In yellow dustbin, pathological cotton waste, beddings, face mask. These type of wastes are thrown in yellow dustbin. Red dustbin include syringe without needles, IV set, gloves, dialysis kit, IV bottles, goggles. And white dustbin include needles, syringe, blades, etc. And blue dustbin include glass, broken glass, lab slides, and metals like nails, metallic body implants, and scissors. According to the Ministry of Environment and Forest, about 4,05,702 kg biomedical waste generated every day in India, out of which around 72% is disposed of. However, more than 28% is biomedical waste is left unattended. Now, biomedical waste used in construction industry. Researches are being carried out to develop suitable alternatives to the construction material. New materials are being used to replace the old ones, improve the durability, strength, aesthetics, and economy. Biomedical waste ash is majorly used in two places: concrete manufacturing and road construction. Why we need of this work? Inadequate management of waste produced in healthcare facilities causes a direct health hazards on the general public, the healthcare workers, and on the environment. Risk of infection outside hospital for waste handlers and scavengers, and at the time uh, and at times general public living in the vicinity of drugs which have been disposed of being repacked and sold off to unsuspecting buyers. Risk of air, water, and soil pollution directly due to the waste or due to defective incineration, emission, and ash. Now, use of biomedical waste in concrete manufacturing. From research paper 232100869, in which tests were performed by Udit Kumar, Vikas Srivastava, and Amit Kumar Singh. They test workability of concrete using biomedical waste. Workability. The concrete which can be placed compacted easily without any segregation is known as workability. Now, table number 2. It is evident from table that workability of concrete decreased with increase in replacement level. Means this may be due to the reason that being lighter than cement, biomedical waste ash occupies more volume than cement on equal weight basis, resulting which more water is needed for lubrication, thereby decreases in workability result. Biomed means cement is lighter than biomedical waste and which is lighter than cement. Now, in table number 2, we can see the workability from slum cone test, and from here we can conclude that biomedical waste ash can effectively used in concrete market. Workability of biomedical waste is less than conventional concrete. Now, conventional. Now, as workability is inversely proportional to strength. Means if workability will decrease, then strength will increase. Means as we increase the percentage, as we increase the level of replacement of percentage of biomedical waste ash, workability will increase, workability will decrease, but strength will increase. Now, compressive strength. Compressive strength, it is the maximum compressive strength that under a gradually applied load a given solid material can sustain without fracture. Compressive strength is calculated by dividing the maximum load by the cross-sectional area of a specimen in a compression test. It is observed from table number 3 that compressive strength of concrete specimens at 7 days and 28 days are increased with replacement level up to 10%. It achieved maximum strength at 4 to 5%. The advantages of biomedical waste concrete is to reducing the level of biomedical waste, and it can be effectively used in concrete making for the purpose of increase in strength and also reducing the cost. For adding superplasticizer, it will act as a good binding property and also develop bonding between biomedical waste and coarse aggregate. Here are the benefits of using biomedical waste in construction. Places used. Derawasi in Punjab is implementing use of biomedical waste ash in construction. Second, Zerion concrete bricks, a startup by Rupam Chaudhary, David Pratim Gogoi and Masum Talukdar, and they are guided by IIM Calcutta. Zerion. Replace red brick with the fly ash, biomedical waste ash and plastic brick, and reduce construction time 25%. This brick is thermal and sound insulation, earthquake and fire resistance. Means the concrete bricks means the Zerion concrete bricks are more usable, and the strength of Zerion concrete bricks are more than normal red brick, and the Zerion concrete brick and the weight of Zerion concrete brick is 8 kg and strength of this brick is 4 to 5 megapascal. And third, where the biomedical waste are used in construction in Abu Bakr Tawafa Balewa University in Bauchi. Now, use of plastics in use of biomedical waste in construction. Road construction. Use of plastic waste in road construction. Swami suggested that plastic waste consisting of carry bags, cups and other utilized plastic could be used as a coating over aggregates, and this coated stone could be used for road construction. Sultana and Prasad investigated the potential use of waste plastic as a modifier for asphalt, concrete and cement concrete pavement. Gawande reviewed technique to use plastic waste for construction purpose of roads and flexible pavements. The research done by Bhagirathi in which plastic modified mixed specimens with plastic contents and different percent by weight of bitumen were prepared through dry process by adding plastic to heated aggregates. Marshall test was conducted on plastic modified mixed specimen to find out optimum plastic content. Following tests on aggregate were done. Aggregate crushing value test, aggregate impact value test, Los Angeles abrasion test. Following conclusions are drawn from study. Marshall stability value of plastic modified mix was found to be 51% more than that for the normal mix, which indicates an increase in load carrying capacity. Aggregate impact value showed a percentage reduction of 17.7 on coating. This means that plastic coated aggregates have better impact resistance. The permanent strain was reduced by 0.21% for plastic modified mix. Average tensile stiffness modulus value of plastic modified mix is found to increase by 47.8% than the normal mix, which indicates an increase in the tensile strength. Here is the figure, NSS College Engineering Road Palakkad, which is made of plastic. It is also known as plastic road. And figure number 2, sample of bitumen road made by biomedical waste. These are the references I used in this presentation. Thank you.